So we talked about Roche's theorem, right? Which said that if we have some function f, right, and we have some curve, let's just write it down. So if we had given some f into the complex numbers and a simple closed curve, gamma, and holomorphic function, everything's holomorphic. Then a number of zeros of f in the interior of gamma is equal to number of zeros of f plus g if we have this following property that that f absolute value is bigger than g absolute value on the curve gamma, right? That was Roche's theorem. So we have some closed curve gamma like this, right? And we think of, well, the way to think of g is as being a perturbation of f. So we add something to f, which is g, which is perturbing it, but not too much, right? So this is what f is doing, say. So f is sending this curve, say it's winding around 0 this many times. And if we have the f plus g is such that whatever point we're at, f plus g has distance closer to the path than to 0, so it's forced to wrap around the same number of times around 0. Yeah? So f plus g, I'm going to draw it like this, just to like make it really simple. So f plus g is forced to wrap around the same number of times. Okay, and then we know by the argument principle the number of times that the image curve wraps around 0 is the number of zeros inside the interior. So that's how this theorem worked, right? And I had this physical model, maybe I still have it up, no, I put it away, of a piece of string here which was going round, and the longer piece of string was f, and the shorter piece of string was g, and as I wrapped around like this with the longer piece of string, no matter what g did, it was forced, it was such that f plus g was forced to wrap around the same number of times as f. Yeah, that's Roche's theorem. So the statement seems maybe a little bit unnatural to begin with, but if you think about how it's proved and what it actually is saying, then it's actually pretty natural. Yeah, it's actually pretty natural. So that's Roche's theorem, and we're going to use this for some cool consequences, and the first one of which is the open mapping theorem. Suppose omega is open, and f from omega to c is holomorphic, then the image of f acting on omega is open too. Okay, and mappings that have this property that when you take the image of open sets, they form open sets. Those things are called open mappings. So in other words, holomorphic mappings are open mappings. So let's put a definition down here. And just generally in any kind of context, if g goes from x to whatever y, and g of s is open for any open s contained within omega, then G is an open mapping. So what this theorem is essentially saying is that F is an open mapping. Okay, proof. All right, so let's draw a picture. We have the image here of F of omega, and the claim that it's open is the claim that whatever point we take inside, we have some little ball around that inside the actual image, right? So let's pick some arbitrary point W. So pick W belonging to omega. We're going to show that there exists a ball around W that's fully inside the image of F acting on omega. Okay, so since F belongs to the image like this, so since it is inside the image, actually let's call it W0. Need W later. Then some point maps onto it, perhaps many points, but at least one point maps onto it, and pick Z0 such that doesn't matter which one you pick, but just pick one. And there might just be one, but who knows? Okay, so we can pick something like this. So consider this map. Capital F of Z, which will be equal to F of Z minus W0. This is a nicely holomorphic mapping, right? And has a 0 at Z0. Yeah? So Z0 is somewhere inside the domain. So let's put the domain over here. So this here is Z0, and we're mapping from omega into F of omega like this. Yeah? So capital F has a Z0, capital F has a 0 at Z0. Yeah? Yeah? But the 0 has to be isolated because it's a holomorphic mapping, right? So it's an isolated 0. So therefore there exists some radius r such that on the boundary of a ball of radius r, there are no other zeros of capital F. Yeah, because it's isolated. Yeah, so is the empty set. Okay, and that means that if we look at little f, no, let's not say it that way. That means if we take the absolute value of this guy, capital F, then the absolute value has to be strictly bigger than 0 on the boundary, the empty set, on the boundary of the ball. Because if that wasn't true by compactness, we could find a point such that it actually was a 0. Right? So thus is bigger than delta for all z belong to the boundary of the ball of radius r around z0 for some delta. Doesn't matter how small it is. Right, so what have we got? We've got some little radius r around z0. And the image of this guy cannot get too close to omega 0. It has to be at least delta away from omega 0, right? Because that's exactly what this thing says. You with me? Give me a thumbs up. Okay, good. So we don't know much about the image of the boundary of this ball. We do know it stays away from W0 by at least delta. So let's suppose it wraps around twice, whatever. Yeah? Maybe it wraps around once, maybe it wraps around 57 times. But we do know that the image is at least delta away from this thing. So bigger than delta. Yeah? Okay, so with this picture in mind, the natural thing to do is to argue that if we put a ball of radius, say delta over 2, around W0, then everything inside that ball will actually be inside the image of f of omega. That's what we'd expect somehow, right? That'd be the natural thing to expect from this picture. Yeah? And that's what we're going to try and argue. So we're going to try and show that if we put a ball of radius delta over 2 around W0, it'll actually be inside the entire image of f acting on omega. Okay? So let's put that as a claim. Or let's say what we're going to do. We will show okay, and if we do that, then we're done, because that means that we have some ball which is completely contained within omega around our arbitrary point W0. Yeah? So let me see if I can erase just half of the board. It's probably not going to work. Okay, I'm going to erase the entire board, and we'll just start from this point. Okay, let's pick up where we're going. So, where we left off. So this is our picture. So I'm going to make a small picture and then a bigger picture. So this is omega. This is, say, Z0. This is the image. This is W0. And we found some radius r like this. Okay, where the image of this thing was, say, wrapping around 2 times like this. And it was always at least delta away. Okay, and this is radius r over here. Cool. All right, so this is where we were. Yeah, and we will show. So our claim was the following. Or I said we will show, but okay, claim that the ball of radius delta over 2 of W0 is actually contained within the entire thing. And that's what we need to show to complete the proof. Okay, cool. All right, so proof of claim. Pick some arbitrary W inside this ball of radius delta over 2 around W0. Okay, and consider the mapping f of z minus W. Okay, and we're going to break this up into f of z minus W0 plus W0 minus W. Okay, and I look at these things separately like this. So this f of z minus W0, previously we called this capital F. So let's write this as capital F of z, and let's write this thing, which is just a constant function, right? Having picked the W0, let's write this as g of z. Is just this constant function W0 minus W, which is a nice holomorphic function. Yeah? And recall f of z was little f of z. Yeah? That's how we define f, which is also a holomorphic function. And note, that the capital F of this thing, for any z around the boundary of the ball of radius r around z0, is bigger than delta for any z. This is how we found this delta, right? And by construction, since W0 is inside the ball of radius delta over 2 around W0, this guy is just equal to delta over 2 for every single z, right? Every single z no matter where, because it's just a constant function, but let's just write it like this. Okay, let's just write it like this. So, capital F of z, absolute value, is bigger than capital G of z for all z belonging to the boundary of this thing. Yeah? Cool. So you can see where this is going, right? So, by Roche. The winding number, not the winding number, the number of zeros of capital F inside the ball of radius r around Z0 is the same as the number of zeros of capital F plus G, right? It's exactly the statement of Roche's theorem, and capital F plus G is exactly this function, f of z minus w. Let's put the z's in because it looks strange without the z. Yeah? Inside. And there is at least one zero of capital F inside this ball of radius r around Z0 because that's how we set it up. Is zero, right? That's how we set things up, yeah? So definition, yeah? So there is at least one zero of capital F plus capital G, i.e. of this thing. Yeah? i.e. there exists R inside this ball. There exists Z inside this ball of radius R around Z0 such that capital F of Z is equal to W. And that's it. Yeah? So we've shown that if we take, let's blow up this picture here. So I'm going to blow this up over here. If we have a ball of radius delta over 2 around this point W0, so this is W0 here, and this is the radius delta over 2, then every single W inside here, so we pick some W right at the start of the argument, just picked one, right? Then there exists some guy, so now we're going to blow up over here, so this is Z0 and this is the ball of radius R. There has to exist some Z which is mapping onto this guy right here. Let's put the Z with leading nearest. Made a mess. There's some Z which maps onto it, right? That's exactly the statement of what we've just shown. Yeah? And therefore, this entire solid ball of radius delta over 2 is contained within the image. Yeah? And which proves the claim. So, which proves the claim. Okay, so this proof is kind of clever, and let's make some remarks. So, firstly, if we had this situation where z0 happened to be a point where the derivative was non-zero, then this is kind of trivial, because if the derivative is non-zero, then locally the function is well approximated by this affine mapping, right? So it's no surprise that if we take a very small ball, it's going to actually cover the point W0 with some kind of shape, right? And in fact, since we're doing holomorphic mappings, and the derivative will be just this mapping which dilates and translates space. If we take the image of a small ball on a small scale, it's another small ball, right? And it will definitely contain W0. So if this was a function that was differentiable at Z0, this is not hard to prove. This is kind of not surprising. Do you see what I mean? Yeah? If it was differentiable with non-zero derivative. Yeah? I mean, you all did multivariable calculus, right? So you learned about the inverse function theorem, right? That if you have a point where the function has derivative or determinant of its derivative non-zero, then it's locally invertible around this point. Yeah, yeah, and you needed specifically that the derivative or the determinant was non-zero, which implies the derivative is non-zero, so that the image of a small ball was actually something that contained your image point, and you could reverse back from it. All right, so if you look back at the proof of that, you'll see that inside the proof of that is the claim that we can contain any small ball around the image with something. And it's just not hard, it's just using differentiability. Yeah? Does that make sense to you? Yeah, give me a thumbs up if that seems some sort of meaningful. Okay, cool. The difficulty arises if we don't have a non-zero derivative at Z0. Yeah? But if we don't have a non-zero derivative at Z0, then what kind of thing do we have? Well, most likely we have something which is like this, where we have the function capital F equals f of z minus W0 has a zero here, and if it has a non-zero derivative, then the order of the zero will be bigger than 1, right? So this will be like z minus z0 to some number m times g of z, right? If the first derivative of this guy was non-zero at z0, yeah, where m is bigger than or equal to 2. Yeah? Because then if we differentiate this, then the derivative will also be 0 at z0. Yeah? And in this case, well, we have very well-behaved function. We have a very well understandable function, because what is this doing on a small scale? It is just taking this ball, and this thing is more and more just like a constant as we approach Z0. So it's taking this ball and it's wrapping it around. It's wrapping it around m times, and then it's sticking it back here. Let me say that better. So this thing by itself is just taking this ball and wrapping it around m times, but the actual function f is taking this ball, wrapping it around itself m times, and then sticking it over here. So it'd still expect that the image would contain a small ball over here. Yeah? So if you wanted to, you could just use this fact and work more carefully with your hands. When I say work with your hands, it means do elementary arguments, don't use powerful theorems, and show that no matter what m is, then the image of a small ball around Z0, the image of a small ball around Z0 will contain a small ball around W0. Because look, if we just consider this mapping, so consider f of z equals z to the m, yeah, then what is it? So 0 is sent to 0 in this mapping, but if we consider a small ball of radius r around 0, this is mapped to a small ball of radius r to the m. Yeah? Yeah? And that's the worst thing that this thing can do in terms of compressing space, right? Yeah? Yeah? So if I just ask you to prove this theorem for this mapping, then where the derivative is non-zero, which is anywhere away from 0, then it's fine, it's easy to do because well, I just argued that it's locally approximated by its first tangent. But at 0 itself, we can still do it because the structure of the way this thing is collapsing space is incredibly regulated. It's collapsing space in a very orderly way. Is that making sense? Yeah? And this is we have such powerful theorems about the way these functions behave at any arbitrary 0. If it's collapsing space, it's also collapsing space in a way which is basically analogous to this. Yeah? So it can't do anything weird. It can't take the image of a ball and just like squash it down to nothing. Yeah? The worst it can do is take the image of a ball and wrap it around itself lots of times and make it smaller that way. But it can't just evaporate space, right? Which an arbitrary mapping from Rm to Rm can easily do. It's trivial to come up with examples, but these guys can't. Yeah? So this is a slick proof using the fact that we have Roche's theorem, and it's this tool we have, so we use it. And it might seem a little bit unnatural because it almost seems like it's overkill because this function g we define is just a constant function, and we have this trivial equality. So it seems odd to use Roche's theorem here in a way, but if you think about what Roche's theorem does, then it's just about the fact that capital F plus G is forced to wrap around the same number of times as capital F, and it's really not that far away from these kind of ideas. So if you want to do an elementary proof like this, using this fact that the worst that can happen is when you have something like this at 0, you'd be arguing in a way which is somewhat following this. So this is the modern way to, like, this is what happens to proof. So as time evolves, people find slicker and slicker ways to go straight to the point. But the heart of the issue here is exactly these things, and particularly this example. It's about the way that holomorphic mappings can squash down space, and they can't squash it down in any particularly strange way. They squash it down in a very regulated way. Okay, cool. So that is this theorem, and it has some strong consequences, which we're about to see. Theorem. Suppose f from omega is holomorphic, then there does not exist such that the absolute value of z0 is equal to the supremum of f of z belong to omega. Okay, proof. All right. So tell me why that sounds like it should be true. Let's draw a picture. So we have a set omega. We are mapping it over here. Okay? So whatever 0 is, suppose 0 is here. Then on this picture, what would be the z that maximizes this quantity? I mean, what would be the point that maximizes this quantity? It'd be like this point over here, right? So this distance here, so there should be at right angles, didn't really do this right. So this distance here would be the thing that gives this quantity right here. So this thing would be the supremum Yeah? Cool. All right. So our claim is there exists no Z0 which achieves this thing. Okay. So suppose that wasn't true. Suppose that wasn't true. That means what? That means that we have some Z0, yeah, that achieves this. And it might occur in numerous places, right? There could be more than one place which achieves this. But in our picture, I've just drawn one, right? Yeah. So in our picture, if there exists a Z0 such that this is true, where is f of Z0? Where is f of Z0 in that case? Yeah, it would have to be here, right? So if there exists a Z0 such that f of Z0 achieves this thing, it would have to exist here. Yeah? Yeah? So let's argue by contradiction. So suppose this is false. Okay, so on our picture, this is where the Z0 would have to be. Right? Sorry, not the Z0, such that the f of Z0 would have to be. Right? F of Z0 has to be here. Yeah? And why do we not believe f of Z0 can be here? It should be an open set. So this thing should have a ball around it. Right? So there should be a ball around this point inside of our set like this. Yeah? And if there was a ball around this guy, then this would not actually achieve the maximum, right? This would not achieve the maximum. So from the pictures, this theorem is really not surprising at all. Yeah? This is not surprising at all. Yeah? But now what we're going to do is we're going to describe these pictures in the language of maths to create a proof. Yeah? Which is what we do essentially all the time, but in this case it's really rather directly from the picture. So suppose such that there is true, then for some delta bigger than 0, we have the ball of radius delta around f of Z0 is actually contained within f of omega, because f of omega is open. But then consider the point like this. So consider say W0, which is equal to f of Z0 plus delta times f of Z0 over absolute value f of Z0. So what am I doing? Let's do a delta over 2. So what am I doing? So here is f of Z0. Over here is somewhere like 0, right? So I'm taking the direction f of Z0 over absolute value f of Z0. So the unit vector in this direction, and I'm moving things forward up to here. Yeah? So therefore, this point right here, which is f of Z0 plus delta f of Z0 over absolute value f of Z0, this guy for sure is further away from 0 than f of Z0, because I've moved in the same direction. Yeah? Yeah, see what I mean? So this point is inside the ball, because it's only moving by delta over 2. Yeah? So for some, say, let's call it Z1 inside omega, we have that f of Z1 actually is W0. Actually, since we're going 1, let's call this W1. So f of Z1 equals W1. and absolute value f of z1 is, what is it? Well, this thing, it's the absolute value of just w1, and what is that? That is equal to absolute value f of z0 1 plus delta over 2 f of z0, like this, yeah? Like this, absolute value, and then this is absolute value f of z0 times this quantity, and that is strictly bigger than this thing, which is meant to be the supremum over omega f of z, like this. So that's a contradiction, right? So we find a point inside omega which is bigger than the supremum of the absolute value of all of f inside omega. Contradiction. So this is not possible. So we cannot find. So the theorem is proved. Yeah, there cannot possibly be a z0 such that f of z0 achieves this maximum, this supremum right here. Yeah, and it's rather easy consequence. So writing it out in the language is somewhat long, but it's exactly this picture I've drawn here, right? Exactly this picture I've drawn here. Cool. All right. So this is called the maximum modulus principle, and it's actually a special case of a more general theorem for harmonic functions. So recall what a harmonic function is. So recall, use harmonic if and only if the Laplacian of u is equal to 0, i.e., so in 2 dimensions, second derivative with respect to x of u plus the second derivative with respect to y of u is equal to 0. Okay, and we learned that these things satisfy the mean value property. So we learned in the sense that I told you this, and I showed you that if it does that, the fact that this is true for harmonic functions implies Cauchy integral formula for holomorphic functions. Right? So we have this. And we know that if we take 1 over 2 pi r, and then we integrate around the boundary of the ball of radius r around x of our function, and we integrate with we do this one-dimensional curve integral, which I'm going to write with respect to Hausdorff measure, because this is the proper way to do this, then this thing is exactly equal to the value in the center, right? This is this property I told you, that if we take some circle and we average around the boundary of the circle, it exactly equals the values in the center. And we thought about this as as the steady state of the heat equation, and I said you can see, or your intuition tells you that that should be true. If we have heat flowing from a hot place to a cold place, right? Then if we take a circle, then some points will be colder and some parts will be hotter, right? And it's not counterintuitive that the thing in the center will be something in the middle of what's around the outside. And in fact, it's exactly an average. Yeah. So this is the mean value property for harmonic functions. Okay, and I claim that this implies the same thing. And from this, there cannot be a x0 such that the absolute value of u of x0 is equal to the supremum over whatever domain we have of absolute value. Okay, so tell me why you believe that. Why from this thing here, the mean value property, so this is mean value property, proper, why do we have the same thing? Try and visualize the situation. Think of a function of two variables as being a mountain landscape always, right? So the x and the y on the table, and u of x, y is the height above the table or below the table if it's negative. Yeah? And give yourself a positive function just to make life easier. Yeah? Okay, so why is this true as a constant mean value theorem? Right, yeah. I have to say that, yeah. You cannot be constant. Thanks. If u is non-constant. So, we have a non-constant u. Tell me why it's true. Yeah. You're thinking of a sequence of steps we could use, but tell me geometrically why. Geometrically why. So you're on a mountain landscape. Suppose you arrive at your point x0, which is the absolute top of the mountain. Yeah? It's the absolute top of the mountain. And it's not at the edge of your planet. So you're not on the edge of, so you're, or let's make a metaphor like this. So you have an island, okay? You're walking on your island, it's a mountainous island, and you get to the top of the highest mountain on the island, and it's not on the coast, it's actually in the center, or it's away from the coast of the island. Yeah? But the island's mountains are harmonic, they satisfy the mean value property. So you're standing there on the top of the highest mountain, and you're thinking something's wrong because, so here's the sideways picture of you standing here on the top of the mountain. Yeah? But you satisfy the mean value property, right? Which means if you look down and you draw some circle around yourself and you average the height around the circle of the mountain, right? That thing should be the same as your height, yeah? But you're on the top of the mountain. So if you look at the circle around you, every point is actually underneath you, right? It's beneath you, yeah? So there's no way the average of the things that are beneath your feet can possibly be the same height as your feet. Do you see what I mean? Yeah? Cool. Right. So you're looking from the sideways, if you look at the circle underneath you, or any circle, then you see this thing, and it's actually directly underneath you, right? So it can't possibly be the case that the average of those values, you know? And then expressing that idea in the language of maths is exactly the sequence of steps that Jaime said. So let me draw the mountain again over here on this side. So this is the mountain, this is you standing right here on the top. And what do we do? So we have that absolute value u of x0 is the absolute value of the average around the outside. So 1 over 2 pi r, the integral, I have to redraw it again a third time, integral of, around the boundary of the ball of radius x0 of u of z, dh1 of z, absolute value. Let's take the absolute value signs inside the integral. So we have 1 over 2 pi I, 2 pi r, and then this integral like this. And then this thing is less than the supremum of u over the entire domain, right? That's less than the supremum of absolute value of u over omega, dh1 of z. This thing no longer depends on z, we can pull it out. So then we just have that this is just the supremum of absolute value of u over over omega. So we have that u of x0 is less than the supremum. It can't possibly be equal to the supremum because we actually have strict inequalities here. So as we do this step to this step, it's actually a strict inequality because this is where the function is strictly less than where we were before. Yeah? So we have that this guy is strictly less than the supremum, where it's supposed to achieve it, so contradiction. So, yeah, this is exactly just expressing the geometrical idea in the language of maths, right? Yeah. And I'd rather you first have the geometrical idea and then you express it, rather than think in terms of inequalities that you can do to achieve the goal. First have the picture and then use the picture as your guide. Yeah? And often the picture exactly tells you what to do. And even when there's no direct, I mean, this is a literal translation of the picture, and so is this. And even when there isn't a literal translation of the picture, it's usually because there's been some kind of simplification and optimization. And you can still prove it just directly following the picture if you have clear enough pictures. Okay. So that's it for consequences of all of these things are consequences of the argument principle, right? So the Roschi's theorem is a consequence of the argument principle, and the open mapping theorem is a consequence of Roschi's theorem, and then this maximum modulus principle is a consequence of the argument principle. The argument principle gives a lot of strong things. Now we're going to change topic slightly, and we're going to talk about homotopies and then this concept of simply connectedness. We're going to formulate the most general version of Cauchy's theorem that we can. So let's start with what we mean by homotopy. So given open set omega and two curves with the same endpoint, gamma 0 and gamma 1. So we have that gamma 0 of A equals gamma 1 of A, say, is alpha, and gamma 0 of B is equal to gamma 1 of B equals beta, okay? Where both of them are inside our domain. Then we say they're homotopic. If and only if there exists a family of curves gamma S from AB into this thing such that, which satisfy the following properties. Okay, first property. They all share the same endpoints. So gamma S of A is equal to alpha for all, let me do both at the same time. Gamma A equals alpha and gamma S of B is equal to beta for all s between 0 and 1. Second property, their image is always contained within omega. So gamma s of AB is indeed contained within omega for all s between 0 and 1. And the third property, if we define this function capital F of s of t to be equal to gamma s of t, then f, which is going from 0, 1 cross product to AB into omega, is jointly continuous. On this set, 0, 1 cross, i.e. it's continuous with respect to the product topology on this set here. Okay, so lots of words and symbols, but let's draw the picture, which clarifies everything. Right, so we have some starting point here, alpha, and some ending point here, beta, and we have a curve. Say this is gamma 0. And we have another curve. Say this is gamma, this is gamma 1. And what this condition says is that we have this family of curves which smoothly goes from one to the other, okay, which slowly deforms from 0 up to 1. So let's say this is S0, and then there's to be another one. So this is gamma S1, and say this is another one, gamma S2, and so on. It's smoothly deformed from one to the other, okay, where they remain inside the region everywhere. And when we create this mapping of two variables, f of s and t, then it is jointly continuous. It's a continuous mapping from here into omega itself. Okay, cool. That's what it says. And the point of this is that we can do this basically when there's no hole inside our region, which these gamma 0 and gamma 1 wrap around. So if we had some region, so this is all inside our region here. If we had a region with a hole like this, and we had gamma 1 does this, or gamma 0 does this, and gamma 1 does this, there's no way to smoothly deform from one to the other with this family like this without some problem. There's just no way to do it. You'll have a discontinuity somewhere, right? Yeah. So they're homotopic if we can smoothly deform and remain inside our set like this. Yeah. Cool. So this is our theorem. If f is holomorphic, on omega, and gamma 1, or gamma 0 and gamma 1 are homotopic, then this integral around gamma 0, f dz, is actually equal to this integral. Okay, this is what's true. Okay, all right, so what's the idea behind this? Well, in this picture, it's not that surprising, right? Because you can see all of this stuff is contained within some region, which I've defined as delta good, which is a region that doesn't contain holes, right? So if we go up with gamma 0 and go back with gamma 1, then that thing will just be a closed curve inside a delta good region, right? Or even simpler, suppose this thing was all happening inside a ball, yeah? Suppose this was all happening inside a ball, then for sure this is true, right? So there's no surprise here, yeah? The point of this is that we're now doing this for any set at all, any open set at all. And our only condition is that we can smoothly deform one to the other, yeah? And it's still going to remain true. It's still going to remain true, okay? All right, so yeah, let's prove this theorem. Okay, proof. Okay, first note. Capital F, this mapping which we defined, I'll put it over here. Capital F of ST, again, was defined like this. So capital F acting on this thing, 0, 1, cross product AB, is the continuous image of a compact set, so it's compact, right? So it's compact inside omega, because each one of these paths is inside omega, yeah? So that's clearly true. So there exists epsilon bigger than 0, such that the distance between this thing and the complement of omega is bigger than epsilon. I'll erase this now. Right, so this is this basic topological property we've talked about, used several times. If we have an open set, we have a compact set inside it, then there's a strict distance between the compact set inside it and the complement of the open set, just by the compactness argument. Yeah? Cool. So there is this delta such that this thing, so F of this thing will kind of look like this. Is strictly inside. Yeah? Okay, so we're going to show that we can prove the theorem if we move slightly from one S to the other. And we're going to start by just moving from S0 to S something a bit bigger than 0. Okay, so take the first path, 0, 1. This itself is a compact set, so we're going to cover it with balls of size epsilon. So let me call this thing 2 epsilon so I have some space to work with. And cover of radius epsilon. Okay, and because it's compact and these are open balls, there are just finitely many needed to cover it, right? So by compactness, you need finitely many. And let's call them B1, B2, B3 up to BP. B1, B2 up to BP. And let's draw a picture. So this is our first path, like this. And we're covering it with balls of size epsilon. And there are finitely many. Right? Cool. All right. Now, if we take path gamma S, it starts in the same place and it ends in the same place. And as S gets closer and closer to 0, this path is uniformly more and more close to the path gamma 0 by this joint continuity. So look, this is what it looks like. Yeah? Cool. Now, I'm going to draw this again, and then I'm going to draw it just with 3 balls because the argument's the same if we have 3 balls or if we have just 1,000,000 or 10, 100 trillion balls. It's all going to be exactly the same argument. So let's do this picture again over here. So this is our path gamma 0. And we're covering it with now just 3 balls. Okay. And we find another path, gamma s, which is very close by. Okay, cool. So what we're going to do is we're going to pick points carefully. So we're going to pick a point here. Let's call that Z1. And we're going to pick a point here, W1. Okay? And we're going to pick a point here. Let's call that Z2. And we're going to pick a point here, W2. Okay? And then we're going to break up this integral into separate curves. And now I wish I'd drawn a bigger picture. Okay. If this picture is too small for you to see what I'm about to do, then just tell me and I erase and I do it again. So this is what we're going to do. We're going to take these separate paths. We're going to go up like this, across from Z1, from W1 to Z1 like this, and then back. Okay? And then we're going to take another path. So this is going to be the path gamma 1. Then we're going to take another path that goes, we're always going anti-clockwise. It's going to go from Z1 to W1, and it's going to go up like this, and it's going to go across, and it's going to go down. And this path will be gamma 2. And then we're going to take another path. Oh, I'm sorry, I should have gone up here. Like this. And we're going to take another path, again, going anti-clockwise, up like this, and then down like this, and then across. And that's going to be gamma 3. Okay? And so we claim that integral of the sum from I is equal to 1 to 3 of f of, integral of gamma I, f of z dz is the same as the integral going up like this along gamma s and then back along gamma 0. So it's the integral of gamma s, f of z. And since we're going back in the opposite direction, it's now minus the integral of gamma 0, f of z. Because it's the same stuff we've done lots of times, that as we go around like this and across and then back, and as we go round, 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 and then like this point, this part of the path joining gamma 1 to gamma to Z1, this point is travel over twice in opposite directions as we sum over all 3 of these things. Yeah? And the same here. So as we go up like this, across, and then back, we cover it with gamma 2, and then as we go like this, we cover it with gamma 3, but go in the opposite direction, so it wipes itself out. Yeah? So the only thing that's left is going up like this, and then going back like this. Everybody with me here? Yeah? Cool. And if we look at each ball, then we are in good shape, because this thing is just a nice closed path inside a ball where the function's holomorphic, right? So we claim this just by cancellation of just by cancellation. And for each I, we actually have that integral of gamma I f of z dz is equal to 0 because it's a closed path inside a ball. Okay. Cool. So that means we have exactly what we want. We have that gamma of s f of z dz is indeed gamma of 0 f of z dz. Yeah? Okay. And what did we require for this? We needed to take s small enough so that we could actually just pick these points inside these overlapping balls here, like this. Yeah? But we have finitely many balls, so these overlapping regions are of finite smallness, right? They could be very small, but there's finitely many of them, so their smallness doesn't go down to 0. So we can just pick our points z1, z2 inside these overlaps, and because as s gets towards 0, the path gamma of s uniformly gets close to the path gamma 0, we can indeed find a point gamma 1 inside the same overlap and a point gamma 2, start that again, a point w1 inside the same overlap and a point w2 inside the same overlap. I'm mixing w with gamma because this is also gamma, so sorry for this. Yeah? So is it clear to you that we can find w1 and w2 such that we can do this by the fact that gamma of s is uniformly close to gamma of 0 as we let s get towards 0. Yeah? And that's a property of joint continuity of the function. Cool, so this is true. And the s which we did this for could be very small potentially, right? Because we don't have any control about how small these regions are. They could overlap in an inconvenient way. But the point is that they are finitely many, so we can find an s which is true. Yeah? All right, so if you think about this argument a bit carefully, this is also going to work if we just take some arbitrary s between 0 and 1 and take another s which is close by it, right? So by the same argument, for any s between 0 and 1, there exists delta bigger than 0 such that any, let's say, s tilde inside the neighborhood, or let's write it like, since it's just numbers, let's not use ball notation, let's do this. Then integral of gamma of s f of z dz is the same as integral gamma of s tilde f of z dz. Yeah? Because once we pick our s and we take our collection of balls covering it, all we need is any other path which is sufficiently close that we can pick neighboring points to our z1, z2, whatever, inside the other path. And we can always guarantee that because since this is open, we can put a little ball around each z1 and eventually there'll be some s such that all the other s's close enough will intersect that ball, right? So by easy arguments, this is true. Are you happy with this? Yeah? Cool. So what does that mean? That means that if we consider the set of all s such that this identity is true, yeah, then the set of all such s's is actually going to be an open set. It's actually going to be an open set. Yeah? Because if you pick any S such that this is true, there is just a tiny neighborhood around that S for which any S close enough to it also satisfies this, and therefore it's an open set. Yeah? Cool. All right. So once again, the set of S's that satisfy this is an open set from this argument. I'm going to raise the board. Tell me how we complete the proof when the board is raised. Well, as soon as you can, actually. So we have shown that let's call this pi, which is the set of S between 0 and 1, such that, oops, gamma of S, f of C, C equals gamma of 0. I should say it's relatively open because it's open inside this compact set. So okay, so if we could show that actually 1 belongs to this set, then we're all fine, right? Because that's exactly the statement we're looking for. Yeah? So how do we continue this proof? Think about a situation where we had something like this before. So we want something to hold true for some wide range, and we can show that if it holds true at some point, we can perturb it a little bit and it still holds true. And we claim that allows us to go all the way from the start to the end. But there was another property that was needed. This is a very useful trick if you just have this in mind all the time. This helps you prove lots of things. Well, the other property is that pi is closed. It's also a closed set by continuity. So by the fact that these guys this mapping f of s of t is continuous on and f is holomorphic. So as s gets closer and closer to some other value, yeah, so i.e. if sk tends to s tilde, then the supremum over 0, 1 of the absolute value of sk minus s tilde goes to 0. Otherwise, we could extract a subsequence for which we would not have continuity of this mapping here, right? And that means that if this is gamma s tilde, and we have this thing is incredibly close to it, right? The limit as k tends to infinity of integral sk is equal to this thing here. Yeah. The same argument actually shows that these things are equal for small enough k, for large enough k, for sk small enough to s tilde. Yeah. So it's a closed set. So gamma tilde is also closed. Thus, pi is open and closed in 0, 1. And if we have a set which is both open and closed inside a connected set, then it's the entire set. And is indeed this thing. Yeah, cool. All right, so this has powerful consequences. This means that we don't have to, this will allow us to define a class of domains, which we're going to call simply connected, where this is the optimal class of domains for which we have that there exists a primitive for an arbitrary function, and therefore all the machinery starts to kick in. So just a final minute. So we say omega is simply connected if for any two paths gamma 1, gamma 0 in omega with the same endpoints, of course. They are homotopic. All right, so if we have a hole in our region, then it's definitely not simply connected because we can find these two paths with the same endpoints inside our region, which are not homotopic. We cannot deform one to the other. Right? But if that's not the case, so this is not simply connected, then they are simply connected. And simply connectedness, it's the beginning of algebraic topology. It's the simplest. It's saying it in the language of math that your region cannot have a hole. Your region cannot have a hole, which is kind of, to us it seems rather easy to say, to define that something can't have a hole. But if we want to be very careful about what we mean by that for any arbitrary set, we have to be precise in what we mean. And the precise way to say it is with this setup, that for any two paths that have the same endpoints inside our open set, they are homotopic to each other. We can deform one to the other. And simply connected sets are the largest class for which we do have all the theorems we've been carefully proving for particular domains. So we'll have that there exists a primitive for an arbitrary function. We'll have that Cauchy integral formula holds true. We'll have that that Gauss-Stats theorem holds true. So all this stuff which I was carefully setting in certain domains, the most general class of domains I talked about before was what I called delta good domains, right? Which were these things which were made up of blocks, such that if you take the complement of all the blocks not inside your thing, then that thing is connected and unbounded, right? That was just a crude way of saying you have something that doesn't contain holes, right? But now we have a sophisticated way of saying something that doesn't contain holes, and it's the optimal, because if it does contain a hole, then all this stuff is false. If it does contain a hole, then it's just not true. We don't have Gauss-Stats theorem, as you know well. I mean, if we have a hole, then if the hole contains 0, for example, then it's not the case that if we integrate 1 over z dz, it's not equal to 0, right? Yeah, so this is not equal to 0. So Gauss-Stats theorem is not true if we have a hole, right? So 1 over z is indeed holomorphic inside this thing, yeah, but Gauss-Stats theorem is not true, yeah. But if we have a function which is holomorphic on a simply connected set, then Gauss-Stats theorem actually is true. All the machinery does follow. Okay, so this is where this is going, and we'll talk more about this on Thursday. All right, so that's enough for today. Have a great day. See you all Thursday.